December 7th, 1941, 07:53 hours, and Lieutenant Commander Shigeru Itaya leads 43 Mitsubishi Zero fighters toward Pearl Harbor, watching the Hawaiian coastline emerge from the morning mist as his formation approaches at 14,000 feet. The Zeros accompanying the first wave of bombers represent the pinnacle of Japanese aeronautical engineering, aircraft so advanced that American intelligence analysts dismissed early reports of their capabilities as impossible exaggerations. What the American pilots scrambling to defend Pearl Harbor cannot possibly know, what no Allied aviator could imagine as they watch these sleek silver fighters diving toward them with deadly grace. Is that the secret to the Zero's dominance lies not in some revolutionary design concept or mystical Japanese engineering philosophy, but in a closely guarded aluminum alloy developed in a Sumitomo metal laboratory 5 years earlier? An alloy so advanced that American metallurgists will spend years trying to understand how Japanese scientists created what was, in 1941, the strongest and lightest aircraft aluminum in the world. And the story of how America discovered this secret, reverse-engineered it, and ultimately used it to defeat the very aircraft it was designed to create, represents one of the most significant intelligence coups and technological achievements of the Pacific War. The Zero's development begins not with dreams of air superiority or carrier operations, but with an impossible set of specifications issued by the Imperial Japanese Navy in October 1937. The Navy staff, watching the performance of their current fighter, the Mitsubishi A5M, in combat over China, demand an aircraft that can fly faster, climb higher, fight longer, and range farther than any fighter in existence, all while operating from aircraft carriers with limited deck space. The specifications call for a maximum speed of 310 miles per hour at 13,000 feet, a climb to 10,000 feet in 9.5 minutes, endurance of 2 hours at normal power or 6 to 8 hours with drop tanks, armament consisting of 2 20mm cannons and 2 7.7mm machine guns, complete radio equipment, and the ability to outmaneuver any opponent in dogfighting. These requirements seem so impossible that Nakajima Aircraft, one of Japan's premier manufacturers, examines the specifications for exactly 1 week before withdrawing from the competition, their engineers concluding that no aircraft could possibly meet these demands with available technology and engines. But at Mitsubishi Heavy Industries, chief designer Jiro Horikoshi studies the requirements and reaches a different conclusion, understanding that the only way to achieve such performance is through radical weight reduction, cutting every possible gram from the airframe while maintaining structural strength. Horikoshi's obsession with weight becomes legendary within Mitsubishi as he weighs components to the nearest gram, questions every rivet, challenges every structural member, searching for ways to lighten his aircraft without compromising its ability to withstand the stresses of combat maneuvering. The typical approach to aircraft design in 1937 involves building structures strong enough to handle anticipated loads with substantial safety margins, using proven aluminum alloys like duralumin or the newer super duralumin developed by Alcoa in America. But Horikoshi understands that following conventional wisdom will produce a conventional fighter, heavier and slower than the Navy demands, unable to achieve the range and maneuverability that will make it superior to anything in the skies over China or the Pacific. He needs something better than duralumin, something stronger and lighter, something that will allow him to build an airframe that seems impossible by the standards of 1937. And this is when fate, in the form of a Mitsubishi purchasing agent named Kimura, intervenes with news that changes everything. Kimura wanders over to Horikoshi's desk one afternoon in 1938, mentioning casually that Sumitomo Metal Industries has developed a new aluminum alloy, something experimental they call extra super duralumin, an alloy reportedly stronger than anything currently available. Horikoshi's interest catches immediately because he has been searching for exactly such a material, something that will allow him to build lighter wing spars, the single heaviest structural component in any aircraft. The wing spars on fighters like the A5M are massive aluminum beams running from wingtip to wingtip, providing the structural strength to support the wings during violent combat maneuvers, and these spars can weigh hundreds of kilograms, limiting how light the overall aircraft can be. If Sumitomo has truly developed an alloy stronger than super duralumin, Horikoshi can build spars that are 30% lighter, while maintaining the same strength, shaving critical weight from the airframe and allowing him to meet the Navy's impossible specifications. He contacts Sumitomo immediately, requesting samples and technical data, beginning a collaboration that will change the nature of aerial warfare in the Pacific. The extra super duralumin that Horikoshi discovers represents a breakthrough in metallurgical science, achieved through years of research by Dr. Igarashi at Sumitomo Metal Industries. The Japanese Navy, understanding that air power will determine the outcome of future wars, had specifically commissioned Sumitomo in the early 1930s to develop an aluminum alloy stronger than Alcoa's 24S super duralumin, which had tensile strength of about 518 megapascals or 53 kilograms per square millimeter. The Navy demanded an alloy with tensile strength exceeding 588 megapascals or 60 kilograms per square millimeter, a 20% improvement over the best American alloy, and they wanted it to be lighter and more ductile, allowing it to be formed into complex shapes without cracking. Dr. Igarashi and his team worked for years experimenting with different combinations of aluminum, zinc, magnesium, and copper, conducting thousands of tests, studying how different heat treatments affected the alloy's properties, slowly discovering that by carefully controlling the composition and processing, they could create an aluminum alloy that exceeded the Navy's requirements. By 1936, they succeeded, producing extra super duralumin with tensile strength of 610 megapascals, making it the strongest aircraft aluminum alloy in the world. The metallurgical breakthrough that makes extra super duralumin possible involves understanding how aluminum atoms interact with zinc, magnesium, and copper atoms at the microscopic level, creating precipitates that strengthen the metal without making it brittle. The exact composition remains a closely guarded secret, known only to a handful of Sumitomo metallurgists and Navy officials, because Japan understands that this alloy represents a strategic advantage that could tip the balance of power in any future conflict. When Horikoshi receives his first samples and begins testing them, he discovers that extra super duralumin allows him to build wing spars that are 30% lighter than spars made from conventional super duralumin while providing equal or greater strength. This weight savings is as extraordinary, allowing him to meet the Navy's performance requirements that seemed impossible just months earlier. He immediately incorporates extra super duralumin into the Zero's design, using it for the main wing spars, certain critical fittings, and other highly stressed components where strength-to-weight ratio matters most. But extra super duralumin has a critical weakness that will eventually contribute to the Zero's vulnerability. A weakness that Horikoshi and the Sumitomo metallurgists understand, but accept as an unavoidable trade-off for achieving superior strength and lightweight. The alloy is extremely susceptible to corrosion, particularly in the saltwater environment where carrier-based aircraft operate with the zinc content that makes it strong, also making it reactive to moisture and salt. Left unprotected, extra super duralumin components will begin corroding within weeks, the aluminum turning to powder as oxidation attacks the metal at the molecular level, destroying the structural strength that made the alloy valuable. Sumitomo develops a zinc chromate anti-corrosion coating that must be applied to every extra super duralumin component after fabrication, a greenish cream-colored paint that becomes the characteristic color of Japanese naval aircraft. This coating provides adequate protection during the Zero's early operational life, but as the war progresses and aircraft remain in service longer, operating in harsh tropical conditions, the coating breaks down and corrosion begins eating away at the wing spars and structural members, weakening Zeros that survive combat only to become structurally unsound from hidden internal corrosion. Horikoshi's weight reduction program extends far beyond the revolutionary alloy, encompassing every aspect of the Zero's design in ways that will eventually prove both a blessing and a curse. He eliminates pilot armor entirely, reasoning that the weight of steel plates behind the pilot's seat and around the engine would compromise the aircraft's performance, and that Japanese pilots, trained in the samurai tradition, should not need armor to do their duty. He refuses to install self-sealing fuel tanks, which American and British fighters are beginning to adopt, because the rubber layers and protective coatings add hundreds of pounds and reduce fuel capacity. He uses thinner aluminum skin throughout the fuselage, as thin as 0.032 inches in some areas compared to 0.04 or even 0.0305 inches on American fighters, because thinner skin means less weight even though it provides less protection against bullets and shrapnel. Every decision Horikoshi makes serves the singular goal of reducing weight to achieve the performance the Navy demands, and when the first A6M prototype rolls out of the Mitsubishi factory in March 1939, it weighs approximately 5,200 pounds fully loaded, more than 2,700 pounds lighter than the American F4F Wildcat that will eventually oppose it, a weight difference equivalent to carrying an entire extra crew member plus full ammunition. The Zero's combat debut in China during July 1940 reveals immediately that Horikoshi has created something extraordinary. An aircraft that outperforms every fighter it encounters so completely that Chinese pilots begin refusing to engage. The Zero's climb rate allows it to reach altitude faster than Chinese fighters can react. Its maneuverability permits turns so tight that pursuing aircraft cannot follow. Its range enables it to escort bombers on missions that seemed impossible for single-engine fighters, and its firepower from two 20mm cannons proves devastating against aircraft designed when 8mm machine guns were standard armament. In the first months of operations over China, Zero pilots achieved kill ratios exceeding 12-1, shooting down nearly 100 Chinese aircraft while losing only 2 Zeros to friendly fire, not a single Zero falling to enemy action. These results seem so incredible that American military observers in China, watching Zero operations and interviewing survivors, file reports describing an aircraft with impossible performance characteristics, reports that intelligence analysts in Washington dismiss as exaggerations or Chinese propaganda designed to excuse their losses. Claire Chennault, leading the American volunteer group that will become famous as the Flying Tigers, writes detailed reports in 1940 warning that Japan has developed a fighter with performance superior to any American aircraft, describing the Zero's speed, climb, range, and maneuverability in terms that should alarm the Department of War. But analysts examining Chennault's reports conclude they describe aerodynamic impossibilities, that no aircraft could combine such range with such maneuverability, that claims of carrier fighters flying escort missions hundreds of miles inland must be fabrications because everyone knows carrier aircraft lack the range for such operations. The Department of War files Chennault's reports as arrant nonsense, refusing to believe that Japan, a nation Americans view as industrially backward and incapable of innovative engineering, could develop an aircraft ahead of anything flying in America or Europe. This institutional racism and arrogance will cost American lives in the opening months of the Pacific War when pilots flying obsolete Brewster Buffaloes and Curtiss P-40S discover too late that everything Chennault reported was true and that they face an opponent far superior to anything their training prepared them to fight. The attack on Pearl Harbor introduces the Zero to American forces in the most dramatic and devastating way possible, as 43 Zeros of the first wave strafe airfields, shooting down the handful of American fighters that managed to take off, demonstrating performance that seems magical to pilots who survived the encounters. American pilots describe watching Zeros turn inside their defensive maneuvers, unable to believe aircraft can change direction so quickly, climbing away from attacks that should have left them vulnerable, appearing over battlefields hundreds of miles from the nearest Japanese carrier in defiance of every assumption about fighter aircraft range. In the months following Pearl Harbor, as Japan sweeps across the Pacific, conquering the Philippines, Malaya, the Dutch East Indies, and threatening Australia, the Zero becomes the symbol of Japanese air power, an aircraft that appears invincible, destroying Allied fighters wherever they meet. The psychological impact of facing an aircraft so clearly superior to everything the Allies can field proves nearly as devastating as the physical destruction, as Allied pilots lose confidence, questioning whether they can ever hope to defeat an enemy with such overwhelming technical advantage. The mythology surrounding the Zero grows with each engagement as Allied pilots search for explanations that make sense of their losses. Some claim the Zero must be made of bamboo to achieve such lightweight and maneuverability, refusing to believe that Japanese metallurgists could develop aluminum alloys superior to American materials. Others insist the Zero must be copied from captured American or European designs, because everyone knows Asians cannot innovate, only imitate. These racist assumptions persist despite mounting evidence that the Zero represents genuinely revolutionary engineering, that Jiro Horikoshi and his team created something original and advanced, that Japanese industry in the late 1930s had reached a level of sophistication that Western observers refused to acknowledge. The myth of the Zero as some kind of mystery ship with strange powers grows throughout 1942, fostered by the aircraft's ability to appear far from any known Japanese base, by its superiority in combat, and by Allied reluctance to credit Japanese engineers with creating a world-class fighter. June 4, 1942 brings the first crack in the Zero's invincibility during the Battle of Midway, where American dive bombers sink 4 Japanese carriers in 5 minutes, destroying not just the ships but the experienced Zero pilots who represented Japan's irreplaceable advantage. But the real breakthrough for American intelligence comes exactly 1 month later on July 11th. when an American salvage team exploring Akutan Island in Alaska's Aleutian Chain discovers something that will change the entire character of the Pacific Air War. Flight Petty Officer Tadayoshi Koga had attempted an emergency landing on Akutan after his Zero was hit by anti-aircraft fire during a raid on Dutch Harbour on June 4th, losing oil and seeking any flat ground where he might set down safely. But the terrain that looked solid from altitude turned out to be soft tundra, and when Koga's Zero touched down it flipped forward, the sudden deceleration breaking Koga's neck and killing him instantly, while leaving his aircraft relatively intact, upside down in the mud but structurally sound. Koga's wingman, seeing the crash and hoping he survived, violated Japanese doctrine, requiring them to destroy disabled aircraft, flying away and leaving the Zero where it lay, intact and filled with secrets. The salvage team finding Koga's Zero understands immediately that they have discovered something extraordinary, the first intact Zero captured by Allied forces, an aircraft that can be restored to flying condition and tested to discover its strengths and weaknesses. They carefully extract the Zero from the Aleutian mud, crate it, and ship it to Naval Air Station North Island in San Diego, where engineers and test pilots begin the painstaking process of restoring it to airworthy condition. The work takes months as mechanics fabricate replacement parts, clean and repair the engine, restore control surfaces, their efforts guided by the understanding that this aircraft represents the key to defeating Japanese air power. And as they work on the Zero, examining every component, studying every structural detail, American engineers discover the extra super duralumin, finding the main wing spars made from an aluminum alloy, unlike anything they have seen, stronger and lighter than the American super duralumin, marked with Japanese characters that identify it as a Sumitomo product but provide no clue about its composition or manufacturing process. The discovery of extra super duralumin in Koga's Zero triggers an immediate intelligence operation as American metallurgists begin analyzing samples, conducting spectroscopic tests, strength measurements, examining the alloy's microstructure under electron microscopes, trying to determine exactly what makes this Japanese aluminum superior to American materials. They discover it contains zinc, magnesium, copper and aluminum in proportions different from any American alloy, with heat treatment and aging processes that create a precipitation-hardened structure providing exceptional strength to weight ratio. This information goes immediately to Alcoa, America's premier aluminum producer, with orders to develop an equivalent or superior alloy as quickly as possible, because American aircraft designers need access to the same materials technology Japan has been using since the Zero's development. Alcoa's metallurgists, working with data from the captured Zero and their own research, develop alloy 7075 in 1943, an aluminum-zinc-magnesium-copper alloy with properties matching or exceeding extra super duralumin, an alloy that will become the standard aircraft aluminum for the rest of the war and remain in use today as the most common high-strength aluminum alloy in aerospace applications. Lieutenant Commander Eddie Sanders takes the restored Akutan Zero up for its first test flight on September 20th, 1942, 2 months after its capture, beginning a series of 24 flights that will expose every aspect of the Zero's performance, revealing both its extraordinary capabilities and its critical vulnerabilities. Sanders flies the Zero against every American fighter type, conducting mock dogfights, testing acceleration, climbing ability, dive performance, turning radius at various speeds, compiling data that will inform the tactical doctrines that save countless American lives. The test flights confirm what combat pilots have been reporting, that the Zero can indeed out-turn any American fighter at low speeds, that it climbs faster than anything in the American inventory, that its range exceeds what aeronautical engineers thought possible for a single-engine fighter. But the tests also reveal fatal weaknesses that experienced Japanese pilots can minimize, but that become critical vulnerabilities when exploited by pilots who understand them. The Zero's lightweight construction and lack of pilot armor mean that concentrated fire from heavy machine guns can tear it apart, with the thin aluminum skin providing almost no protection, and the unprotected fuel tanks igniting instantly when hit by incendiary rounds. The large ailerons that give the Zero its extraordinary low-speed maneuverability become liabilities at high speed because the control forces required to deflect them against airflow become too great for pilots to overcome without hydraulic assistance that the Zero lacks, meaning the aircraft that can turn on a dime at 200 miles per hour becomes sluggish and unresponsive at 350 miles per hour. The carburetor design causes the engine to cut out during negative G maneuvers, meaning a Zero diving to escape cannot push over into a negative G dive without the engine sputtering, forcing the pilot to roll inverted and pull through, wasting precious seconds during which a pursuing American can close the distance. These weaknesses, revealed through systematic testing of the captured Zero, lead directly to the tactical doctrines that will defeat Japanese air power, doctrines based not on trying to outmaneuver the Zero, but on exploiting its vulnerabilities through superior speed, firepower, and pilot protection. The intelligence gained from Koga's Zero flows immediately to American aircraft manufacturers and directly influences the development of the F-6F Hellcat, the fighter that will dominate the Pacific skies from 1943 onward. Grumman engineers studying data from the captured Zero and combat reports from early Pacific battles understand that trying to build an American Zero would be a mistake, that American industrial strength and pilot training philosophy favored different solutions. Roy Grumman decides to build a fighter heavier and more powerful than the Zero, accepting that it will not match the Zero's low-speed maneuverability, but ensuring it will be faster, more rugged, better armed, and better protected. The Hellcat emerges from this philosophy as an aircraft 5,600 pounds heavier than the Zero but powered by a 2,000 horsepower Pratt & Whitney R2800 radial engine driving a 3-bladed Hamilton standard propeller, giving it speed and climb performance matching or exceeding the Zero, while incorporating pilot armor, self-sealing fuel tanks, and a robust airframe that can absorb tremendous battle damage and return home. The first encounters between Hellcats and Zeros in late 1943 demonstrate immediately that American industry has solved the Zero problem, that the combination of superior tactics informed by study of the captured Zero and superior equipment designed to exploit the Zero's weaknesses has shifted the balance of air power. Hellcat pilots follow doctrine developed from Sanders' test flights, attacking from high altitude with speed advantage, making a single high-speed pass with concentrated fire from 650 caliber machine guns, then climbing away before the Zero can respond, refusing to engage in the low-speed turning fights where the Zero excels. This boom and zoom tactic proves devastatingly effective as heavily armed Hellcats tear through Zero formations, their pilots confident that their armor and self-sealing tanks will protect them from the Zero's 20mm cannons, while their own firepower will destroy Zeros in single passes. The Hellcat achieves a kill ratio of 19-1 against Zeros and other Japanese fighters, completely reversing the air superiority situation that dominated the first year of the Pacific War. The Zero's decline accelerates throughout 1944 as American industry produces thousands of advanced fighters, including the F-6F Hellcat, F-4U Corsair, and P-38 Lightning, all designed with the knowledge gained from the captured Zero, all incorporating lessons learned from studying Japanese metallurgy and design philosophy. Meanwhile, Japan struggles to develop a Zero replacement, hampered by resource shortages, bombing raids on industrial facilities, the loss of experienced engineers and test pilots, and most critically by the inability to match American advances in metallurgy and manufacturing. The extra super duralumin that gave the Zero its advantage in 1941 becomes a liability by 1944 as corrosion weakens aircraft that remain in service far longer than designed, operating in harsh tropical conditions without adequate maintenance, their wing spars literally turning to powder inside the protective coating. Japanese attempts to develop new fighters incorporating lessons learned from captured American aircraft and combat experience produced designs like the Kawanishi N1K and Mitsubishi J2M, but these aircraft reach frontline units in limited numbers, too late to affect the war's outcome, while the Zero remains in production and service throughout the war simply because Japan lacks the industrial capacity to replace it with something better. The story of American 7075 aluminum represents one side of a broader technological race that Japan ultimately loses because American industrial and scientific infrastructure proves superior in the long war of attrition. While Dr. Igarashi and his team at Sumitomo developed extra super duralumin in secret laboratories, achieving a breakthrough that gave Japan a temporary advantage, American metallurgists at Alcoa and other companies conduct systematic research programs involving thousands of scientists and engineers testing thousands of alloy combinations, supported by universities, government laboratories, and industrial research centers that Japan cannot match. When Americans capture the Zero and discover extra super duralumin, they reverse engineer it within a year and put improved versions into mass production, demonstrating an adaptive capacity that Japan's more centralized and resource-constrained system cannot equal. By 1944, American fighters incorporate not just 7075 aluminum but advanced welding techniques, improved heat treatments, better corrosion protection, and manufacturing processes that allow production rates Japan cannot approach. The captured Zero's influence extends beyond fighter design to affect every aspect of American Pacific strategy, as commanders understand that Japanese air power, once seemingly invincible, can be defeated through superior tactics, equipment, and pilot training. The doctrines developed from Sanders' test flights spread throughout the Pacific Fleet and Army Air Forces, with every fighter pilot receiving instruction on how to fight Zeros, learning to use altitude and speed advantage, to avoid low-speed turning fights, to make high-speed diving attacks, to work in pairs using the THAC weave where wingmen protect each other, covering angles the Zero's maneuverability might exploit. These tactics, combined with the Hellcat's superior performance and protection, transform air combat in the Pacific from desperate defensive battles where American pilots felt outclassed to systematic destruction of Japanese air power, where well-trained Americans flying superior equipment dominate the skies. The final irony of the Zero story comes in 1945 as the last Zeros fly kamikaze missions, their pilots deliberately crashing into American ships because Japanese commanders understand their fighters can no longer compete in conventional combat against American opponents. The aircraft that dominated Pacific skies in 1941, with its superior performance and innovative metallurgy, has become obsolete, outclassed by American fighters incorporating technology reverse-engineered from the captured Akutan Zero, flown by pilots trained using tactics developed from study of that same aircraft. The extra super duralumin that gave Horikoshi the strength-to-weight ratio he needed to meet the Navy's impossible specifications in 1937 has become 7075 aluminum, the standard aerospace alloy, with Japanese innovations absorbed into American industrial production and improved through systematic research. Flight Petty Officer Koga, dying instantly in his crash landing on Akutan Island, could not have known that his failure to destroy his disabled aircraft as doctrine required would contribute more to Japan's defeat than any single combat action, providing Americans with the knowledge they needed to crack the Zero's secrets and develop the weapons and tactics that would sweep Japanese air power from the Pacific skies. Today, aviation historians and metallurgists study the Zero as an example of how technological advantage can shift dramatically during wartime, how innovations that provide dominance at war's beginning can be copied, improved and turned against their creators by opponents with superior industrial and scientific infrastructure. The few surviving Zeros, preserved in museums or maintained in flying condition by dedicated enthusiasts, stand as testament to Jiro Horikoshi's genius and to the Sumitomo metallurgists who developed extra super duralumin, but also as reminders that technological superiority alone cannot win wars when the enemy possesses the capacity to learn, adapt and respond with superior resources. The greenish cream colour that marks Zero fighters, the zinc chromate coating protecting their revolutionary aluminum alloy, serves as visible evidence of innovation that changed aviation history, an alloy that gave Japan temporary air superiority and ultimately contributed to the development of modern aerospace materials through the process of capture, analysis and improvement that characterizes technological warfare. And somewhere in a museum archive, samples of extra super duralumin cut from Koga's Zero remain preserved, the physical evidence of metallurgical breakthrough that helped Japan dominate Pacific skies until American industry cracked its secret and turned that knowledge into the weapons that defeated the Zero and the empire it defended.